Okay, this slide completely says about the iteration procedure. So we are going to have a series of solution now up to second order, and there will be an assignment for you for your third order. Okay, now we'll see. This is the equation. We know already to 6.54 this equation. Okay, the same equation we have written here. Okay, now I am going to consider this term as a green function. I am going to consider this term as a green function, which is G. This is potential energy, so V. This is your psi. So I am going to replace this equation by G, V, psi as it is like this. So your mu will be, psi will be like this, your psi naught will be like this, and minus mu divided by 2 pi h bar square. This term is termed as G, this is your V, this is your psi. Okay, to find the first order approximation. So already we have found out the zeroth order. So now we are going to find out the first order. For the first order approximation, you just replace psi by psi naught. That's all. So just replace psi by psi naught. So you will have two terms. Okay. Now for the second order, you replace psi naught by psi 1. You replace psi naught by psi 1. For the first order, what we have done? We have done is just replace psi by psi naught. Psi naught. Okay. For the second order, replace psi naught by psi 1. That's all. For the third order, you replace psi 1 by psi 2. So it goes on until input and output to be equal. That is called the iteration process. So now we will go for the first. Clearly we will explain. So now psi naught is replaced by psi incident. Of course we know that psi naught is nothing but psi incident. So we can replace with psi incident, which is nothing but your plane wave equation. So we know this one. And the same thing, we have written the same thing, minus mu divided by 2 pi h bar square. Your G is this term, your V is this term, whereas this is for the first order. R is replaced by R1. This is first order. So that's why R is replaced by R1. And of course this is psi naught here. Correct. Here this will become psi naught of R1. Is it okay? So for the first order we have two terms. Okay, is it okay? I repeat. See, G is replaced by this term, okay, in the integral, and V is V of R, but here for the first order, so this must be replaced by V of R1, and your psi of R replaced by psi naught of R1, d cube R1. For the second order, as I said, you will have to replace with psi naught. Instead of psi naught, you will have to replace with psi 1. Okay, psi 1. Already we have psi 1 is here. Okay, now we will see. Psi 2 equals psi naught minus 2 mu h bar square, your GV. What is psi 1 of R? Psi 1 of R is nothing but this one. Psi 1 of R is nothing but, you just replace this one. So you multiply now. Multiply this by this, multiply this by this, you will have three terms. This is the first term. Multiplying this term will give you second term. Multiplying this term will give you third term. For the second order you will have three terms. Then for the third order you will have four terms. That's all. It goes on until the input and output should be equal. So the part we call this is iteration process. Is it okay? Simple idea. So this is about Born series. So this is equation 6.54. So the total wave function is nothing but unperturbed incident wave function. So these are all perturbed wave function, and of course we have taken only first order perturbation. So extending to higher orders, so this is your zeroth order, this is for the first order, second order, third order goes on. Your GV is termed as propagator, which propagates from one particle to another particle collision, because this only propagates. Your GV, green function with potential energy. Okay, what we call this as Born series. So this is called a series, Born series. Okay. So now we'll come here. The first order solution is obtained by inserting psi naught of R in the integral. So now just this is your equation which we have obtained earlier. Now we are going to replace this by A e power I k naught R. So this is replaced by this one. Okay, what about your this term? This term will be mu divided by 2 pi h bar square This term is like this. What of V of R1? V of R1 is exactly like this. Psi naught of R1. Psi naught of R1 is nothing but A e power I k naught dot R1. A I have written A here outside. A e power I k naught dot R1 d cube R1. Is it okay? Come on. Is it okay? Now second order solution. Inserting now psi 1 of R. So for the second order we will have 3 terms. For the first order we will have 2 terms. See, we have written 2 terms. For the second order we will have 3 terms. 1, 2, 3. So you have psi incident. Okay, psi naught, which is nothing but psi incident, minus 2 mu by 2 pi h bar squared. Okay. So G, you have written G. B, we have written B of R1. Your psi naught will be replaced by R1. So which is nothing but e power A e power I k naught R1. So A I have written here. Okay. And this term plus mu divided by 2 pi h bar squared. Your GV, G is here, V is here. Okay, GV. Again one more G is here, V is here, and your psi naught will be e power A e power I k naught R2. So A is here. So it goes on. Now look at this equation. Look at this equation. There is no wave function on the right hand side. Earlier in all the expressions we had the wave function on right hand side itself. Okay, now there is no wave function at all on right hand side. Only we have the wave function only on the left hand side. So this is the proper solution. Okay, come on, look at this equation. There is no wave function on the right hand side. So this is the proper solution. So this is the desired order. For any series we can apply. So there is no wave function on the right hand side. Is it okay? You have to be careful with R minus R prime, R minus R1, R1 minus R2 goes on. So this is for the successive order. Okay. First one particle will hit a second particle. Second particle will hit third particle. So we will have to take only these 2 dimensions only, not this dimension. So that's why replaced by R1 minus R2. So next time will be R2 minus R3. So it goes on. Okay, so you have to be more careful with the coordinates. So this is what the idea. I told you that you have an incident particle, it will go and hit the first collision. So R1, this is in terms of position, this is in terms of k space, reciprocal lattice. So this is in terms of position, coordinate space. R1, then we have another collision R1 and R2, another collision R1, R2, R3, goes on. So each successive term in the Born series involves more scattering events. So this is for more successive collisions. Similarly, in k space we have k kinetic energy, and it goes and hits one particle, the particle which comes out with another wave vector k out. So this is another particle. This is also another third particles. Thus we can have multiple scattering. So physically incoming particle undergoes a sequence of multiple scattering events from the potential. So this is the schematic diagram of a multiple scattering. Okay. Now first Born series is given by equation 6.56. So we have done. So this is 6.56. Okay, this is complete one. There is no wave function on the right hand side. So this is the complete correct solution. So which we have obtained now. Okay. Now the mod R minus R1 can be written as exactly like this, which you have already learnt in mathematical physics. Mod R minus R1 can be replaced by R squared minus R1 squared minus 2R1 to the power 1 by 2 under root. Okay. Now I am going to take R squared out. I am going to take R squared out. This is under root, correct? So I am going to take R squared out. So this will become R. Now I am going to take R squared out. So this will become minus R1 squared divided by R squared minus 2R R1 divided by R squared. And we know that already this, we know already about the coordinates. This is your target. This is the origin. This is your target. This is your director. So director is too far. The coordinate between these two is nothing but your R. The coordinate between these two is nothing but your R1. R1 is less than that of see, R1 is less than that of R. So we can write this as R1 by R is very, very less than that of 1. So this will be very, very less than that of 1. We can remove this one. So 1 minus binomial expression. So this will become 1 by 2, 2r r1 by r square. That 2 and this 2 will get cancelled. I repeat, binomial expression, this will become minus 1 by 2, 2r r1 by r square. Okay, this 2 will get cancelled. Just multiply this with r, will give you r minus, already one r is there, here also there. So r squared r1 divided by r squared, this will cancel, you have r minus r1. So mod r minus r1 is replaced by simply r minus r1. So e power I k r minus r1 is replaced by r minus r1. This mod is replaced by r minus r1. Is it okay? Now the integral is in terms of r1. Look at this equation. The integral in terms of r1. So e power I k r is constant. Okay, because we are going to integrate with respect to r1. So your e power I k r is constant. So we can pull it out. That's the idea. So multiply these two will give you e power I k, just to separate e power I k r, e power minus I k r. Other terms only return the same thing. No problem. Now I have pulled e power I k r by r out because it's a constant. Because we are going to integrate with respect to only r1. I repeat, we are going to integrate with respect to r1. So e power I k r by r is a constant one. We can pull it out. So these terms are let it be like this. So you have minus a mu divided by 2 pi h bar square. I have pulled e power I k r by r out. Other terms are I have written exactly like this. So physical realization of first order Born approximation, two things. The target potential is very weak. Of course, earlier itself we assume. If it is very weak, then kinetic energy of the incident particle must be very, very high. Okay. Now, I am going to combine these two. E power I k r, e power I k naught r1. I am going to combine these two. So combining these two will give us e power I k naught minus k. K naught minus k is replaced by del k. So this is replaced by del k. Other terms are let it be like this. Now we can compare this equation with the equation which we learnt already in the first session. Can you remember? This is first session we learnt. Okay, in the first video lecture we learnt about the total wave function is nothing but the wave function of the incident plus the scattered wave function. We are going to compare these two, and this will happen only with the asymptotic solution. R tends to infinity. So you compare these two equations. When you compare, you are going to compare this equation, then we will get f of theta comma phi is equivalent to this term. Okay, other things are equal. See, both are equal. They are equal, and this must be equal. So your f of theta comma phi equals minus mu divided by 2 pi h bar squared integration e power I del k dot r1, correct, v of r1 d cube of r1. So we have found out now scattering amplitude. We started with green function, the solution of starting the time independent equation. We started with wave function, we used green function, okay, and we got the solution. At the end we have obtained scattering amplitude. So this is the idea. So if we know the expression of a scattering amplitude, just square it, that will give you differential cross section. That's the idea. So the integration variable R1 extends over the spatial degrees of freedom of the target. So one can obtain the scattering amplitude for different kinds of potential. Of course, for different kinds of potentials, we can use this one. Okay. So the differential cross section in the first order Born approximation is given by this one, and squaring on both sides will give you differential cross section. Okay. So scattering amplitude is momentum transfer. We have done by means of only Fourier transform, reciprocal lattice. So in K space is nothing but your momentum transfer, momentum space. So that's why scattering amplitude is done only by means of momentum transfer. We get the differential cross section for various potentials. Okay. So this expression shows that the Born scattering amplitude is proportional to the spatial Fourier transform. We have used only Fourier transform technique of scattering potential with respect to momentum transfer. The advantage of the phase shift from the Born approximation is free from the consideration of the boundary condition. Of course, we have not used any boundary condition here. We have not at all used. So it is free from boundary conditions of the wave function. We only need to evaluate the integral. If you are going to evaluate the integral, we can obtain the expression or value of the differential cross section. That's all. Okay. So now we are going to have the last session, which is the condition for the validity of Born approximation. How it is valid, Born approximation is valid or not. So one thing is we assume that weak potential. First we assume the weak potential. Potential is very weak, then kinetic energy must be very large. Whether it is correct or not, we are going to check. So this is the validity of Born approximation. Okay, so very important question. This question also very important question. So the Born approximation is valid only when the total wave function is slightly different from the incident wave. We know already about this. The total wave function will be slightly, because the total wave function consists of plane wave as well as spherical wave equation. Correct? So plane wave plus spherical wave. Superposition of plane wave and spherical wave equation. So it is when the total wave function is slightly different from the incident wave function. It implies that whenever the scattered wave or interaction energy is small compared to the incident term. So this is what we have assumed. Born approximation is valid for psi of r slightly different from the incident plane wave. Second one is the second term is smaller than the first term, because this is interaction term, potential term. So this must be small compared to that of first term. Correct? So this is what we assumed. So it implies that the second term is smaller than that of the first term. So we have already assumed weak potential. Out of weak potential only we got the scattering amplitude. Okay. Now the same thing, whether we are going to check whether it is correct or not. This is called validity of Born approximation. So you just have this term. This is a weak term. Potential energy is very weak. Interaction potential is very weak. This is your incident wave function. It is very, very small. Correct? According to this assumption which we have assumed already earlier. Okay. Now we know that psi incident is nothing but plane wave equation. So we can replace with a e power I k naught r. Left hand side let it be like this. Right hand side is replaced by this one. So squaring this one will give us 1. See, just take the complex conjugate. A e power I k naught r multiplied by a e power I instead of I, so minus I k naught r will give you 1. So right hand side answer will be 1. Okay, yesterday we discussed a star. So e power I k r becomes e power minus I k r. So squaring that will give you answer will be 1. So this is the condition. Okay. Now if r1 equals 0, can you remember I said earlier in the class we will be using this one maybe later. Two properties we learned for the green function. One property is this one. Second property is translation symmetry. Can you remember these two properties? For the spherical symmetry, when r1 equals 0, almost equal to 0, the equation will be green function will be spherical symmetry. That is the first property. And second property is translation symmetry. Correct? R equals r plus a. The first property we have used now. So when r1 equals 0, this equation becomes exactly like this. Okay. So if it is so, this equation will be in terms of spherical symmetry. So we will be using only spherical polar coordinates. Okay. So we are going to use spherical polar coordinates. So when you are going to use spherical polar coordinates, your e power I k r by r, let it be v of r, let it be. So instead of e power I k dot r, you can write, we can write e power I k r cos theta. K dot r becomes k r cos theta. So spherical polar coordinates dq bar is replaced by r squared sin theta dr d theta d phi. Okay, so this is one property. You just separate. So in terms of phi, first we will do it with the phi. So 0 to 2 pi d phi will give you 2 pi. So one integral is over. Second integral with respect to theta. So 0 to pi e power I k r cos theta sin theta d theta. Sin theta d theta. So now we will assume let cos theta equals x. So you will just differentiate, that will give you minus sin theta d theta will be dx. You substitute in this equation. So this equation becomes, now this is in terms of x, correct? This is in terms of theta. So you have to change the limit also. So this becomes cos 0 is 1. So cos 0 is 1. Cos pi is minus 1. Is it okay? See, cos theta equals x we have assumed. So instead of theta, you have to replace 0 first, then theta replaced by pi. So cos pi is minus 1. So limit has been changed now. E power I k r cos theta. So this becomes e power I k r cos theta. Cos theta is nothing but x. So e power I k r x. Sin theta d theta is nothing but minus dx. So minus dx. I repeat, sin theta d theta, which is nothing but minus dx. So minus dx. I am going to change the limit, removing minus sign. I will remove now. And you are going to substitute now. And you are going to integrate now. So e power I k r x divided by I k r. You are going to integrate with respect to x, not r, x by x. So e power I k r x by I k r. Now just to substitute the limit. So instead of x, substitute 1. So that will be e power I k r. So minus e power minus I k r. And this I k r I have pulled out. That's all. Multiply and divide by 2. Multiply and divide by 2. So that will give you 2 e power I k r minus e power minus I k r divided by 2 I k r. Okay. What about e power I k r minus e power minus I k r divided by 2i, which is nothing but sin k r. So 2 sin k r by k r. Is it okay? Now you substitute these two expressions here. So we have the same term. Here also we have same term, except dr. We have not done for dr. We have done only for theta and phi. So e power I k r by r, v of r like this. And first one is d phi. D phi we have replaced by 2 pi. And other term will be 2 sin k r by k r, r square dr, which is very less than that of r. Okay, is it okay? So now what I am going to do is multiply and divide by 2. Okay, multiply and divide by. So this 2 pi gets cancelled. Okay, 2 pi gets cancelled. We have this 2 mu. Okay, comes here. I am going to have h power square divided by 2 mu, and I am going to multiply and divide by k. I repeat, this 2 pi gets cancelled. This k is here somewhere. I can take this k out, and we have 2 mu. We have already k here. I am going to multiply and divide by k. So this becomes k divided by k square h bar square divided by 2 mu. Is it okay? I repeat, 2 pi gets cancelled. Okay, first point. Second one will be 2 mu. I can bring this 2 mu down. So which becomes h bar square divided by 2 mu. This k I have brought it here and multiply and divide by k. So that will give me k divided by k square h bar square divided by 2 mu. Is it okay? And we know already p equals h bar k. So this can be replaced by p squared. P squared by 2 mu. P squared by 2m is nothing but kinetic energy. We know already kinetic energy is nothing but p squared by 2m. Here it is p squared by 2 mu. Is it okay? So I can bring this term to that side. So kinetic energy is very large. It implies that this term, interaction term, is very less, whereas this kinetic energy, I am going to bring this term, so kinetic energy is very large, which we assumed earlier. Kinetic energy of the incident particle is very, very large. So this is the validity of Born approximation. Whatever we have assumed, it's correct. So we assumed weak potential. That means the kinetic of the incident particle is very large. So it clearly says that the kinetic of the incident particle is very large. So this is your interaction energy. Okay. So this becomes, this is the idea. So this is already we have obtained, and this is the expression for your scattering amplitude. So this is your scattering amplitude. The expression for scattering amplitude. Okay. I think last slide. Yeah, last slide. So differential cross section will be just you are going to square the term. Square of scattering amplitude will give you differential cross section. Just to square it. So this is the condition for the validity of Born approximation. So Born approximation is valid for the large incident energy and also for weak scattering potential. The wave integral between incident and scattering potential is very less than that of kinetic energy of the incident particle. So in this class we discussed mainly two things. This is about Born approximation using green function. We have obtained the solution wave function, correct? So we have used green function and also we have used delta function and we have obtained solution of psi, first point. So from their solution we have compared with the solution which we already learned in the last video lecture, that is psi total will be psi incident plus psi scattered. So we have compared these two equations and we have obtained f of theta. Okay, so that's the first one, Born approximation and Born series. Then after that, squaring of scattering amplitude will give differential cross section. And already we assumed that there will be a weak potential, and we have checked whether the weak potential is correct or not. Weak potential means the kinetic energy will be very large. So we have checked, and we have checked the validity of Born approximation. Okay, so that is the end of the class. We will see in the next class.